We're now ready to start looking at the individual steps of the EM expectation maximization algorithm. And as the name suggests, there are two steps. There's the expectation, the so-called E step, and the maximization, the M step. So let's go through the E step first. This is the one that's a little bit more complicated and requires where the probabilities are going to come in. Let me remind you where we are. I give you a bunch of points in our case, two-dimensional, but this can be an arbitrary dimensional space. I also give you an underlying model that is parameterized by whatever, a line, a parabola, a plane, a hyperplane, I don't care. And your job is to do two things. Estimate these model parameters. I'm again going to assume I know how many clusters there are. We'll come back to that at the end again. So estimate the model parameters, A sup 1, B sup 1, A sup 2, B sup 2, and tell me what the assignment is probabilistically of each data point. So what is the likelihood you belong to model 1? What is the likelihood you belong to model 2? Obviously, since there's only two models here, and this is the probability, those will sum to 1. So once I know the probability to belong to model 1, the probability to belong to model 2 is 1 minus that. Okay, so in the E step, we are going to do the same thing we did in k-means. We have this sort of chicken and egg problem. I don't know either, but if I know one, I think I can get to the other. So we're going to do the same thing we did in k-means. We're going to assume we know the model parameters, and all we're going to do is guess those parameters. And then we're going to compute the probability that each point, x sub I, y sub I, belongs to each model, k equals 1 or 2. I'm going to do this for two models in a two-dimensional space. This generalizes very nicely to arbitrary dimensions and arbitrary classes. It's just the notation's a little bit more cumbersome. Okay, so if we were just doing k-means, we wouldn't have to do much work. We would just compute that residual, the vertical distance. We'd do an assignment, and then we'd re-estimate the model parameters, and we'd be done. But we want this probabilistic approach because we're going to acknowledge that this isn't always as clean as two completely separate lines, for example, that are parallel or away from each other. That intersection makes things a little messy, and we want to acknowledge that we want to have uncertainty in our measurements. Okay, so here's what we're going to do. For each data point I, and for each model k, so I is equal to 1 to n, let's call it, and k is just 1, 2, 1, 2, model 1, model 2, compute the residual. Remember what the residual is? I take a point up here, I compute the vertical distance to model 1, that's the first line, I've guessed those parameters. I compute the vertical distance to model 2, I've guessed those parameters, so I have an estimate of the model parameters, if you can call guessing an estimate. And I'm going to just compute the absolute value here. So here it is. The kth model parameterized by A and B, slope and intercept, minus what the y parameter is, and then that is the ith residual for the ith data point for the kth model, k equal to 1 or 2, model 1, model 2. Given this residual, we're now ready to compute the probability. So we're going to ask the following question. Given this residual, for each model k, what is the probability that the point xi, yi belongs to model k? And we can frame this as a conditional probability question. What is the probability that point I belongs to model k, m sub k, given the residual that I just calculated between the ith point and the kth model? Notice, by the way, that for every point I have two residuals because I have two classes. And I'm simply going to ask, what's the probability that this point belongs to model 1? What's the probability it belongs to model 2? Obviously, those have to sum to 1. So in a case of two classes, I only need one of those probabilities. Bayes tells us that that conditional probability can be written as the product of the likelihood in the prior divided by the evidence. Let's go through that. The likelihood is, what's the probability that I see that residual, given that it belongs to the model, which is a statement of how much noise is in the data relative to the model, times the probability that the point belongs to the model to begin with, not just a prior assumption of how many data points belong to model 1 and model 2, divided, of course, by the full evidence, which is what's just the probability or the distribution of residuals that we expect to see regardless of model assignment. So let's work through that Bayesian probability now because we need to compute that conditional probability. All right, I'm just going to redo the probability here. What's the probability I belong to model k given the residual, likelihood, prior, evidence? All right, this, of course, is, I can write this out because this from the law of total probability tells me that the probability of residual I for model K is the following, because I only have two classes. It's the probability of residual I for model 1 given that I belongs to model 1 times the probability that I belongs to model 1 plus the same thing for model 2. This just is what's called the law of total probability. And now let's see, because some of these terms look awfully familiar given this up here. So notice that up top, I have the probability that I belongs to model K, and I have the prior here, and I have the probability that I belongs to model 1, probability that I belongs to model 2, in the numerator and the denominator. So let's just go ahead for simplicity and assume equal priors. That is, let's assume that every data point is just as likely to belong to model 1 as it is to belong to model 2. Now, if it's not, it's fine. You'll have to push through a little bit more of these probabilities. But to simplify the probability estimation here, let's go ahead and assume that. And if I assume that, then my conditional probability that I'm trying to estimate, again, what's the probability that a point belongs to a model given the residual, because that's the goal of the E step, is now simplified. It's the probability of seeing the residual given that it belongs to the model, divided by the sum of those two for model 1 and for model 2. Good. Now, what is this probability? What is the probability of seeing a residual given that it belongs to the model? As I said earlier, that is a statement about what is the noise in the system here that you are expecting. So, for example, if you have no noise in the system, you expect every data point to be exactly on the line, well then this probability had better look a lot like an impulse, right? The residual should be 0 and nothing else. And if it's not 0, well then you don't belong to my model. But of course, that's not really what it's going to look like. There's going to be some slop in the data. And how much slop? Well, we don't necessarily know, and so we're going to do what we almost always do in these situations, is we're going to assume some reasonable distribution. We're going to assume a normal distribution. So I'm going to assume that the amount of noise here is going to be Gaussian. So a lot of things will be near the line, and it'll fall off gently, and it'll fall off with some, I don't know, some sigma here, which, by the way, is going to turn out to be really, really important, and we'll come back to that in a little bit. So let's assume that this probability up top is, I've got my normalization factor up here, 1 over the square root of 2 pi sigma squared, e to the minus, the residual squared for point I, model K, divided by 2 sigma squared. So just a nice, gentle, normal distribution. Now again, what is sigma? We'll come back to that later on when we go to implement this. There's some important details there. All right, so what's the E step do? Assume the model parameters are known. For each data point and each model, compute that residual. Shove that residual into this probability distribution where each of the terms and the numerator and the denominator is simply this. Notice that all of these terms are the same. The only thing that's different is whether it's k is equal to 1, the denominator is the same, or k equals 2, the denominator is the same. Each of these probabilities can be modeled with a Gaussian, where you're simply substituting out the k and the I based on which data point and which model. Okay, so now out of this comes the following. For each data point, given I have some initial estimate of my model parameters, I have a probability. I have a probability that I belong to model 1, and I have a probability I belong to model 2. So notice here, I have not done an actual class assignment. For every data point, I have 2 values associated with it, which is the likelihood that I belong to model 1 and the likelihood or the probability that I belong to model 2. And now the question is, well, I have to re-estimate the model parameters based on those probabilities. And that's what we're going to do in the M step when we come back.